The prepper term is what our notes.
What notes be?
His notes.
Okay. I am going to try something a little different with you guys. I'm going to record these lessons and then make them available to you online so that when you go home to do homework, because I know you're going to go home to do homework, you have this as a resource. If you're looking through your notes and something doesn't make sense, you don't remember what was said, you just need a refresher on the lesson as a whole, then that will be something that's available to you. Yes.
So you're going to edit out the student questions?
Yes. I will definitely try and break it up by examples and stuff to the best of my ability. I can't I have to make it effective, time efficient for me as well. So I will do what I can to make it easy for you guys to work with. But this is just another resource for you as you're trying to prepare. And I don't recommend you save all of these for the night before the test, because we put in a lot of time into this stuff over an entire unit. So use it. I hope that it's something that helps you guys. And if it doesn't help, then I don't know what to say. All right. So today we are starting chapter 4. Chapter 4 still deals with derivatives, so all of your rules and everything you learned last chapter are still necessary. Don't just throw them away. Right? You do need them. But what we're going to talk about is, for the first part of chapter 4, is how the derivative actually tells us about the graph of a function. And we're going to work with derivatives, and we're going to be able to sketch curves based on derivatives. Today, obviously, we're looking at maximum and minimum values of a function. So a lot of graphing at the start of this unit, and then we're going to start talking about maximums and minimums in real life. They're called optimization problems. And that's pretty much what chapter 4 is, but it is an application of the derivative. It helps us understand what it actually does, what it actually tells us about graphs and that kind of thing. So what I want to tell you real quick, there is a lot of writing today. There are a lot of words in this PowerPoint. There are a lot of definitions. And so finding abbreviations that work for you, instead of writing the word maximum every time, please just write max and min, because we need to move through. This right here doesn't need to be written, so don't write it, because I'm not waiting for you to write it. These are just examples to kind of prep you with this lesson. But you need to be efficient in how you write things down today, because we got to get through what we're doing. So all this is are some examples of why we would need to know maximum and minimum of a function. It's the optimization problems that we're going to be working with later on in this chapter, but just to kind of prep you with the reasons why we're finding these things. If we're trying to find the shape of a can that minimizes manufacturing costs, this is something that's actually a project in this class. Yes! Totally getting into projects. Okay, so because if you're the owner of a company that has to produce something that goes in a can, you want to know how to produce that can without spending a whole bunch of money. So there's a way to optimize that, to find the minimum cost.
Is it those cans?
It is those cans, yes. So Coca-Cola and Campbell's don't actually make as cost-effective as they could. What is the maximum acceleration of a space shuttle? The radius of a contracted windpipe that expels air during a cough. An angle that blood vessels branch so to maximize energy expended by the heart. So these are all examples.
Why would you want to know the radius of your windpipe?
If you're any kind of a throat doctor, you certainly want to know the radius of a windpipe.
Who sits around thinking of stuff like this?
Doctors and engineers and those people that make 6 or 7 digits a year. So, although this may seem really far-fetched to you, this really is, there are things that are important, there are things that are studied. This kind of stuff is stuff that you're just told in a textbook, and you guys, this is not an insult, but it gets taken for granted because it's just written on a page. Somebody found it, somebody figured it out, and they worked through stuff to be able to discuss these things and talk about these things. So, anyway, maximum and minimums are important in real life. And so we're going to start with the definition. I'm going to talk while you write. Right? I'm going to kind of, what would be the proper word? Translate this for you. So we have an absolute maximum and minimum, and we're talking about, we'll have two types. We have absolute and local. So an absolute maximum, if this y value at c, at whatever x value, is the highest value in that function, which is pretty self-explanatory. If it's an absolute maximum, it's the highest value that that function reaches. So that means that f of c is greater than or equal to the rest of the function, all of f of x. And we're talking about all values that are in the domain. D references the domain of the function. And then the absolute minimum is the same concept, except now we're talking about some y value that is the absolute lowest that your function reaches. And so that means that f of c, whatever this y value is less than or equal to the rest of f of x. There is no other value that's lower than that. If a question is asking you to find extreme values of a function, it is asking for maximums and minimums. So just having an understanding of that vocabulary word. This is just talking about the minimum value on the domain of our function. All right, can I go on? Get this? All right. So we're looking at a function here. This function ends up here at this point and here at this point, and we want to identify or determine the absolute maximum and the minimum value. So our absolute maximum is at what point on this graph?
About 5. Negative 5, 9.
Negative 5, 9-ish. So this would be our absolute maximum value. It's the highest point that our function reaches on this domain that we're looking at. What about the minimum value? Where would the minimum value be?
3 and 2/3, 3 and 3/4, getting like 7 and 3/4.
Okay. Good. So our absolute minimum is down here. The lowest point that it reaches is somewhere around 3.5-ish, and like negative 7.75-ish. Hi. Sure. That's a ginormous bag of dum-dums. where could I get a bag that size? Right?
You get that many thumbs up.
I don't see it here.
Wow, dude.
She said we're not
Thanks. All right. So I would recommend as a sketch, just to kind of help you visually with the definition you just wrote down, just sketch this. Like draw a little, you don't have to have numbers or anything. All you need to know is that when you're looking at a graph, the maximum obviously is that highest point. That would be considered your absolute maximum, wherever that is. And then your absolute minimum is going to be at the lowest point on that curve. So just so that you have a visual for the definition you just wrote down, this right here would be just that. It's showing you what that definition is explaining. Any questions on the max or min? It's pretty like self-explanatory as far as introducing it. All right, so what we can look at on this same graph here is we can choose to only look at a certain interval. So we would say we're picking one point that we're looking at, and so we're going to kind of zoom in on that, and we're going to really look at a smaller interval and now discuss maximum and minimum values. And so if we're only looking at a small interval here, we can see that we have a minimum value on that interval. Because we're only talking about an interval, that's called a local minimum. It's local because we're zooming in on a certain part of our graph. Okay, and these will have significance as well, knowing these local mins and maxes. Okay, it's not the absolute minimum, it's not the lowest point the graph hits overall, but we can certainly zoom in and say that we have a local minimum. And so knowing that we have this, where do you think we have a local maximum?
Oh, right there.
Right there, yeah, sure. Right there, like around 0.5 and 2-ish. So we would look at that next interval and see that we have a local maximum. Okay, so these are the 4 things that we're going to be looking at: the absolute max, the absolute min, and then our local max and our local min. And we're going to talk about how to find those, how to identify them, and that.
That's the absolute definition of things.
Do you understand the difference? Yeah.
Are we gonna be working more with graphs on this?
Yeah.
A lot of graphs. Okay, so absolute minimum is looking at the entire domain of the function. Local minimum is zooming in on a specific interval to identify a lowest point. So that's exactly what this is talking about right here. We have that local maximum if this point is the highest one of the entire function when we're just looking at the interval. So when x is near c. And then the minimum is the same concept. That point is the lowest point when we're zooming in just on a specific interval. All right, so if we are looking at the function y equals cosine of x, and we're trying to determine the absolute and local maximums and minimums for the function, let's start with maximums. Where would our absolute maximum be? Our absolute maximum is going to be 1. Okay, it's the highest that our graph ever goes. What about local maximum? Local maximum. Still 1, because even if I zoom in on this interval right here, my highest point is at 1. If I choose to zoom in on this interval right here, my highest point is 1. So over the entire domain, the maximum that it ever reaches is 1. And there's no other like high points that we can zoom in and say that that's the highest point on the interval. And so the absolute and local maximums are the same. What about the minimum? Absolute minimum. -1, local minimum. -1. The same thing is true for the minimum values. So this one is a little unique because they all match. It doesn't ever go any higher than the absolute, or than the local maximum values. Never any lower than the local min. All right.
You said him. Sorry, the guy who said don't pull another hammy, and like the word hammy is.
I see.
is another.
All right. Y equals x squared. You got this? Let's start with maximums. Does this graph ever reach a highest point?
No.
No. So there would be no absolute maximum or local maximum for this graph. Can't be infinity. Absolute, maximum, and minimums have values, have numbers. So then what about the minimum values? 0. We have a minimum value at 0, 0. And that would be our absolute and local minimum.
So absolute and local maximum minimums have that number.
They do have to be numbers, yes. Somewhere we get to the actual math of this. Oh. Okay, let's talk about this one real quick. Relative maximum or minimum, same word or same thing as local maximum or minimum. So
So
if
it's
you
neither
see
on all of
asking relative. So relative or absolute maximum means for x to the third.
So it's neither on all.
Third. Okay, this doesn't have any max, doesn't have any min. This right here just kind of flattens out. It doesn't really do much, and then it goes. Okay, so this doesn't have anything. No extreme values.
So basically, anything that has x to any power has neither. So like,
No, because x squared just had a minimum.
oh yeah.
And also, once you get into polynomials, if you have a cubic function, it might do like a loopy thing, and now you've got local maxes and
Oh,
mins.
okay.
This one is just flat. You like that? That's like the formal word for it, actually.
So
It's
y,
better
so if
scientifically
y equals
proven.
so if y equals x, it would be neither
That's
also.
why I do eating on a pizza.
No, don't do
Points for
that.
creativity.
Okay,
Yay, we can do that.
The parameter.
all right, 3x to the fourth minus 16x cubed plus 18x squared. Here is a graph of this function. We're looking for the absolute and relative extreme values, and we're looking at the interval from -1 to 4.
Do we have to derive this?
We will have to derive these. Right now, this is all visual. Okay, but we will have to derive these. So -1 Here's the ending point for this graph to 4 over here. So let's start with the absolute maximum value. Ethan, I want you to tell me where the absolute maximum value is. Where do you see the absolute maximum? These are 30, 10, 20, 30.
Goes by fives.
This graph.
Yes.
Okay, yeah. All right. Caitlin, go see Dr. Schwartz up front.
37?
Good, we have an absolute maximum at 37 right here. It's the highest point this graph reaches. Chi, what about the absolute minimum value? Where do you see that? Good, like negative 27-ish. So we have our absolute minimum down here. The lowest point that our graph goes. Now if we're talking about local extreme values, Tyler, do you see a local maximum anywhere?
What?
We have a local maximum. Okay, so when x is equal to 1, this goes up to about 5, and so we have a local maximum here. Are there any other local maximums? Okay, no other local maximums. And local minimums, Kevin, do you see any local minimums? Good, we have a local minimum right here at 0, 0. One thing to note, you cannot have local maxes or mins on endpoints. Okay, so local maxes and mins have to be like in the middle. They can't ever be endpoints. Any questions on identifying these from a graph? Having an understanding of what these local maxes and mins actually are. Yes.
Do we have to write intervals and decreasing and increasing?
Yeah.
Sweet.
Okay, do you recognize any kind of pattern as we identify these local extreme values? Even from the first graph you looked at, now this graph, we found our local min here, local max here. Anything that you notice about local maxes and mins? Yes.
They're always when it flattens out and it turns in the other direction.
Very good. It's always when our graph flattens out and then starts going in the opposite direction. So we have these little like things one way or another, right? Okay, so that is like visually to understand that that's what's happening with local maxes and mins. I think will help you out a lot when we're talking, when we start getting into the math part of it and not the visual part anymore. Because you will have to work backwards where you start with the equation and you make the graph. The graph is not given to you. Okay, so to know that our maxes and mins are typically happening, or they typically look like this, is an important thing to know. Okay? Questions? Why? What? Really good estimation. Alrighty. So now we have theorems. Now theorems are going to lead us to actually doing the math of this. So we have the extreme value theorem. Like one of the really important things about the extreme value theorem, and anytime we're dealing with theorems, we have to pay attention to like the, what would be the right word? Requirements for the theorem to be used. Okay, for this theorem to be used, f has to be continuous, number one. And it has to be on a closed interval. So the endpoints of our interval have to be included in order for us to even use the extreme value theorem. And so if it's on a closed interval, then the extreme value theorem says that there has to be an absolute maximum and there has to be an absolute minimum at some point in that interval. So as long as it's closed, as long as the function is continuous, there has to be a maximum and a minimum value. This means we should always be looking for one.
that one teacher where everybody goes clapping? He's been quiet this week. Is he gone?
He's been quiet this week. No, he's not.
Only class was
So weird. 'Cause I don't
They're
hear
celebrating their successes.
Why can't we do that?
I feel like I'm celebrating my success.
great on the test.
All right, you're obviously done.
Here.
Wow, that's a really faint purple line. Okay, so we have here a graph, part of a graph. We're looking just at the interval from like 1 to 4.25. Okay, because this is a closed interval, our endpoints are included in the interval that we're talking about, then we have an absolute maximum at the highest point in that interval. Because remember, our absolute extreme values can be endpoints, it's just our local ones that can't be. Okay? So we have an absolute maximum out here, where we have our highest point, and then down here, our absolute minimum is at the lowest point in that interval. So as long as it's continuous, as long as it's closed, then we can definitely identify these extreme values. Any questions on that? Okay, on this function here, we have the interval from A to B. We're looking at a closed interval where our endpoints are included. So our absolute maximum, Catherine, would be where? Absolute maximum. Oh, 8. You're looking at the y value, sorry. Yep, so we've got an absolute maximum somewhere around 1 point something. And 8? Yes.
When we talk about like what maximum and minimum are we like speaking in terms of S values or
So
Should be a point.
it's gonna be the y value that is the max. The maximum this graph reaches is 8. That happens, so we have a maximum value when x equals 1.25.
So the
Does
absolute.
that make sense? So it would be how you choose to word it. If they're asking for the max, like what is the maximum, they're looking for like what is that highest point that it reaches. I would encourage you to always include both pieces of information.
Would you rather as a coordinate?
No, probably you could either use function notation, so f of 1.25 equals 8, or you could say the maximum value is 8 when x equals 1.25. I would discourage the use of a coordinate just because we're using a lot of interval notation, and coordinates often get confused with intervals. Other questions on that? So our maximum is at 8. Danielle, where do we have our minimum value? Somewhere around 2, and that happens when x is equal to like 4 point something. Okay? So extreme value theorem says as long as it's continuous, as long as it's closed, then we're absolutely going to have a maximum and minimum value. So we always need to be looking for those. Okay, this first graph right here, determine the maximum and minimum values for the graphs.
So do I, this is mean we have to have 2 points? Does this mean we have to have 2 different points of min max? No? Okay, so it's gonna be 3,
What is
0. That it stops. That means it has to be less than that number. So it will be 2. That'll be 2. Max value would be 2.
The max value would be 2. Is 2 the highest point this graph ever goes?
it
No.
approaches?
But it approaches.
Oh, it
3.
approaches 3. Can we approach a maximum value? Can we talk about
We can try.
approach it?
We should
No, it
just
has to be dead sensitive.
Okay, so for this graph here, dang it, I knew that was going to come first. There's maximum. Why is there no absolute maximum value?
Because there's discontinuity.
Because it's not a continuous function. So we only have to have these two things if it's continuous, if it's on a closed interval. So if it's not continuous, or it's not an closed interval, we might have a minimum, or we might have a maximum, but we don't have to have those two things. Does that make sense?
So the graph has to be continuous.
In order for us to definitely have both. So it's okay to say that there's no absolute maximum on this one, because it's not continuous. And so the extreme value theorem doesn't apply here. Okay, we do still have an absolute minimum value, because we could just look at this right here, and this is a continuous function on a closed interval. It's the lowest our graph ever goes. Yes.
So why would the one with the black dot not have a maximum?
Because it's not continuous, and so this is the value that's included right here, but this is not the highest point that my graph goes. My graph goes all the way up to here. And once I get up here, now I have a discontinuity. I could also look at this as being an open interval, and so because it's open, like I can't work with that. Yeah.
So I see that the one with the actual point, the black one, is higher than the one with no value. That would be max value.
Then that would be the maximum value, yes, because that's the highest point value. Other questions on this? Okay, what about here?
There's no,
There's neither.
there's no absolute max.
There's an absolute max.
And no
yeah.
local
No,
max.
There's neither.
There's nothing.
It only has a
There's-
capacity.
There's nothing. We have an open point here, and so it's not a closed interval. And then we have an asymptote over here, and so that just keeps going up forever and ever and ever. So there's no absolute maximum, no absolute. Okay. Are we good? I keep saying like there's math coming, and then there's.
I know, I'm waiting for the next
I'm waiting
slide.
for the math too. Okay.
Right here, Cole.
This
This
is
one.
easy.
All right. So, how to actually find these values? We've got a couple different theorems that we're going to be learning about this. And this kind of goes into what we were talking about with how these always look. The local maximums and the local minimums always happen, or typically happen, when the graph is going up and then it flattens out and starts going down, or it's going down and flattens out and starts going back up. And so what do we know about the derivative at those points?
That's a tangent.
Well, sure, it's a tangent line.
It's zero.
What's zero?
The slope.
The slope of those tangent lines is zero, so the derivative is equal to zero. So how are we going to be able to find where we might have a local minimum or a local maximum? How are we going to be able to do that mathematically?
If we set the derivative equal to zero.
We're going to find a derivative, we're going to set it equal to zero. Whatever answer we get, it's going to help us determine like that there might be a local maximum. Bless you. Okay, it doesn't always mean that it is a local max or min. It just means that there could be one there. We have to test that. Okay, so an example of not having one. If we found the derivative of x cubed is our function here, then it's going to equal 0 when x is equal to 0, but we don't actually have a maximum or minimum there. So these just become like test points for us. They help us narrow down where we might have a max or min. It doesn't guarantee that we will. Any questions on that? Yeah.
So we have to plug in 0?
No, you set this equal to 0.
Oh.
This is equal to 0 when x is 0. Yeah. Don't understand
Okay, so.
this. Like maximum or a minimum value when the derivative equals 0. So that's kind of our first step to try and determine where these are at, because we're going to want to find where we have maxes and mins. Yeah, you'll be given a function, not the graph. Well, the max and mins apply to the graph. Yes, that's what we've been looking at. You're not going to be given a graph every time. You're going to be given a function. So we can guess or predict that there could be a max or min value when the derivative equals 0. Because one of the things we talked about was that typically that graph is flattening out and changing directions. And so at some point up there, it has a derivative that's equal to 0. It has its slope that's equal to 0. But what it doesn't guarantee is that it doesn't guarantee that it is a max or min. It just says that it could be at that point. And this would be an example of one that is not actually a maximum or minimum value. And we're going to talk about testing that.
This is more understandable without.
All right. Does that kind of help? The beginning of this was all visual for you to understand, like, visually what's happening. Now we're going to move into how to solve for that. C is any number. C is the number
C is the new
where the derivative equals 0. So for this problem, if I set this equal to 0 and I solve for x equals 0, C is now 0. So it's the number that you find where the derivative is equal to 0. Other questions? I think with an example, Kevin, that might help like make that transition. Okay? So again, all it does is tells us that there's a horizontal tangent line. It does not guarantee that that's a maximum or minimum value.
Oh, crud.
Yay!
What? Oh, I don't know where it came from. Actually, it's part of the graph, I think. The graph is going to come up and that'll be on there. Okay, so another example where this theorem kind of fails. If we have the function absolute value of x, we know what this looks like, right? You know what absolute value of x looks like on a graph?
Yep.
It's a v. And that v has an absolute minimum at 0, right? We can visualize that. We know what that looks like. Can we find the derivative at 0? Let's review. Let's review. This is such a good thing to review because it comes up all the time.
Oh.
If I want to derive the absolute value of x, how do I do it?
Piecewise.
I have to write it as a piecewise function.
Yell it out after.
So if I'm going to write it out as a piecewise function, what does it look like?
X,
Got that.
x and negative x.
Fine then, Tyler, take over.
Okay, I'm going to put negative x and then x.
If,
When is it negative x?
if x is less than 0.
When is it x?
If x is greater than or equal to 0.
You got it. Okay, so this is my function rewritten. This is how we rewrite absolute value. So if I wanted to derive this function, f prime of x, that's a terrible squiggly line. That's the real official term for that symbol too.
That's really cute.
Squiggly.
Okay, so I'm going to derive this function now. Absolute value, piecewise functions, I just derive each piece. So the derivative of negative x is what?
Come on now.
Negative 1. The derivative of x?
1.
1. So this means that my derivative, when x is less than 0, is negative 1. So I just have a straight line going at negative 1. And when x is greater or equal to 0, then it's 1. So can I set this equal to 0? Can I get an answer when I set this equal to 0?
Yes.
The derivative.
You get 1. Well, because if it's x is less Greater than or
I set this equal to 0. So 0 equals -1 when x is less than 0, 1 when x is
Oh.
Where's your one?
Oh my god.
I derived negative x
Equal to 0 is 1.
derivative, so I'm just using the power rule. Huh?
Right?
0.
0 in.
I'm not putting 0 in for x.
Oh.
I'm setting the derivative equal to 0. Not x equals 0. The derivative equals 0. Does the derivative ever equal 0?
No.
No. What two values does the derivative equal?
-1.
Equals -1 or it equals 1. So if I set this equal to 0, am I going to get any answer?
No.
No, I'm going to get no solution. Or that it doesn't exist. So this equation, the derivative doesn't exist. But we know that we have a minimum value. Right?
When you said the limit.
So, not the limit. I mean, the limit doesn't exist, but the derivative at 0 does not exist, but we still have a minimum value. So all of this to say that just because, no, let me rephrase that. The derivative being equal to 0, doing this, setting this equal to 0, is not the only way to find a local max or min. When is the other case that we can have a local max or min, or an absolute max or min? What did we just see right here?
Those are- When
There you
derivative does
Not exist. Okay, so there are two cases when we could have a maximum or minimum value. We could have it when the derivative is equal to 0. That's when we're looking at those functions that have the loopy things. Or when the derivative does not exist. Make sense?
Yeah.
Okay. Those two pieces of information are super important. For how we identify where we might have maxes or mins. Okay? And that's where this definition comes into play. A critical number is those are the values that we check for maximum and minimum values. We have a critical number anytime our derivative is equal to 0. That was the first part of that, or that was the theorem we talked about. Or if the derivative doesn't exist. And these critical numbers are what we check for maximum and minimum values.
Period.
Maybe they were taking notes or something.
Yeah.
What?
Everybody's sick.
Good.
See how he treats us? Where's his friends?
Call me coconut. Last 2 years.
You call me
I will.
Okay, do you have questions about a critical number?
You call me
Two cases when a critical number, or two cases where we have a critical number. What's the first one? When the derivative is equal to 0,
Or it does not.
or when the derivative does not exist. So we're doing a lot of work with our derivatives still. Okay, ready?
What, we Matt now?
Math.
Yay!
Find the critical numbers of f of x equals x to the 3/5 times 4 minus x. So we're given a function here. We want to know where the critical numbers are. Because critical numbers are eventually going to lead us to what? What what do they help us find?
X and B.
They help us find maximum and minimum values. Okay, so critical numbers are important because they're going to eventually lead us to that information. So we're trying to find the critical numbers of this function here. So what do I need to do? Right, I'm deriving the function because I find critical numbers with information from the derivative. And what do I do to derive this? Product rule. Product rule is the first times the derivative of the second. Plus the second x times the derivative of the first. So, derivative of 4 minus x, what is it?
It's negative X.
It's negative 1 times, okay, so x to the 3/5 times negative 1. Then we have 4 minus x times the derivative of x to the 3/5. What's the derivative of x to the 3/5?
3/5 x to the negative 2/5.
3/5 x to the negative 2/5. All right. Do we like this?
No.
No. No, we don't.
Well,
We gotta start simplifying this, right? What can we do?
we can multiply the X and the X1. 3/5 times the negative 1.
Okay, we can multiply that
And
and
then
become negative.
the right side. Or multiply the right side.
What can we do with this over here?
You can distribute 4 minus x times 3 to, or x to the negative 2/5 to the denominator.
Okay? Okay. Did you guys hear that?
No.
Do you have any idea what he just said?
It makes no sense.
What can I do with this?
You can bring to the denominator because it's a negative exponent.
This goes down because it's a negative exponent. So if I'm going to distribute this to this, what am I multiplying this to?
3.
3. I'm just multiplying, or I should have done it the other way. But I'm just multiplying this 3 to what's on the inside. The 5 and the x to the 2/5 are going to be on the bottom.
That's what I said.
We got that?
But she explained it.
So I have negative x to the 3/5, that's the first part. And then I'm going to write this as 12 minus 3x over 5x to the 2/5. Is this pretty yet?
No.
Yes.
It's boring.
It's not pretty. Don't lie to yourself.
Yeah, Tyler.
What do we do?
Comes out.
We need a common we did that all in one. Sorry, Andre.
So you.
We need a common denominator. What's my common denominator?
5x to the 2/5.
Alright, so I'm multiplying this by 5x to the 2/5 on the top and bottom.
Does
Yeah,
that
that
mean
was
we get
gorgeous before,
5x?
now it's just like.
Or negative 5x?
Oh no, it gets pretty. It really does. What happens right here? 5x to the 2/5 times negative x to the 3/5.
It equals 1.
Do you see how much makeup you have to put on this?
So it's going to be negative.
This is why we
It's
just
going to
go
be,
au natural,
it's
everybody.
going to be negative 5x.
Great, what do we do with these exponents?
Minus
You
add
add them together and it becomes 5 over 5, which is just 1. Super pretty, right? So this becomes negative 5x. Then we have plus 12 minus 3x over 5x to the 2/5. See how nice that turned out?
And then you can
You
combine
guys are
the
trying to
terms.
lie to yourselves like this is pretty.
And then combine my terms.
Combine like terms.
Yes.
So
So
you get negative 8x is 12 plus 12 over 5x to the 2/5. Okay, that's the derivative. That's step 1. What are we doing? What's the question asking us?
Critical numbers.
Says
Critical numbers. Where do we have critical numbers?
When we set it equal to 0.
When the derivative equals 0,
And when the derivative does not exist.
or it does not exist. Okay, looking at this. When will the derivative equal 0?
When x equals 0.
When the numerator is 0,
Oh.
not when x equals 0. So the derivative is equal to 0 when x equals, or the numerator equals 0. When does it not exist?
When the denominator is 0.
When the denominator is equal to 0. So we can break this up to find all of our critical numbers. The first thing we do is set the numerator equal to 0, because that's going to tell us when the derivative is equal to 0. So negative 8x plus 12 equals 0.
It's gonna be 3 over 10.
Dude.
So we subtract 12, divide by negative 8.
The denominator is
Stop. Okay, so we have a critical point when x is equal to 3 over 2. And then we set the denominator equal to 0, and that's going to tell us when it doesn't exist. This happens when x equals 0. That's a 0. It kind of looks like a
It's just the
really
way you
sad
said it, so
theme.
dejected, like that's a 0.
Well, look at it. What? That doesn't actually look like a 0, but it is a 0. So these are the critical numbers for the function. And what are the critical numbers going to help us find?
The minimum and the maximum.
Minimum and maximum values. Yes, I'm going to keep asking you guys this until everyone answers the question. Oh,
Oh, something's coming, that's fine.
any questions on this?
How can you tell which is the minimum and which is
That's what we do next.
the, oh.
This is just find the critical numbers.
Great.
Okay, ready for the next part of this? So now we know how to find critical numbers. Critical numbers are when? When do we have critical numbers?
When the derivative is 0 and the derivative does not exist.
When we put so much.
What, JJ?
Limit equals 0. I mean limit. You made me say limit.
Derivative.
Derivative equals 0.
The derivative does not exist.
Derivative does not exist. Okay, so those are critical numbers. What do critical numbers help us find?
Max.
Max and min. Yes. Okay. Ready? Extreme value theorem. Let's revisit that for a second. Extreme value theorem. What do we know about that? Has to be closed. Has to be continuous. And if that's the case, then what do we have? What does the extreme value theorem tell us? You have to have an absolute minimum and an absolute maximum. What are the critical numbers going to help us find?
Minimum and maximum.
Mins and maxes, and those critical numbers are going to be locals. Local maxes and mins. Okay, so critical numbers are not going to be on endpoints. The endpoints come into play with the extreme value. That's not a complete sentence. Oh.
That's why.
Okay, so this right here is the process you're going to use to find absolute maxes and mins. Critical numbers are going to help us with local maxes and mins. The extreme value theorem is going to help us with those absolutes. Okay, step one. Somebody put this in your own words. What are we doing in step one? We're finding the critical numbers. Is that all of step one?
Find
You're
critical
finding
numbers of
when the derivative of does not exist and
Okay, those are your critical numbers. Is that all that we're doing? Are we just finding the critical numbers like we did in the last example?
Nope.
What are we doing?
Also finding the values of the endpoints, determining the biggest ones.
Just this one. Just this set. Finding critical numbers. What did we say for our critical numbers in the last example? What were they? X equals 3 over 2. They were the x values and x equals 0.
About the y values.
Is that what we're doing right here?
No, we gotta find the y values.
Right. Which part of this is telling you to find the y values?
Find the values of f.
Find the values of f. What is f? The function. Find the values of the function at the critical numbers. What does that mean? Plug in your critical numbers into the original function to get the y values, to get the values of the function. You guys understand that? What is second step asking you to do? How do we do that? Find the values of the endpoints. What does that mean? What do we do?
Plug in A for x, plug in B for x.
What's that going to give us? Yes, the y values. You guys understand we're looking at y values? Do you understand that?
Yeah.
When we're talking about... Help me out here. When we're talking about maximum and minimum value, does x equals 3 over 2 and x equals 0 tell me if I have a max or min?
tells you where they are.
Tells you where it might be, but it doesn't actually tell me the maximum or the minimum value. What would make x equals 3 over 2 the place of the maximum value? How would I know that that would be where the max is?
If f of 3 over 2 was the highest point.
If I evaluated my function at 3 over 2, if I plugged in 3 over 2, and I got the highest point in that interval, I got a y value of like 20, and nothing else was higher than 20. So which values of our coordinate tells us about max and min? The y value is what's actually telling us if it's a maximum or a minimum value. Do you guys understand that?
Yeah.
To just find x equals 0 and x equals 3 over 2 doesn't tell us anything about a maximum or minimum value until we plug it in. And once we plug it in, then we have to see if that's the highest value or the lowest value. Does that make sense? So if it's telling you to find the values of f, you actually have to evaluate your function at those points, at the critical numbers and at the endpoints. The endpoints are given to you. It's not a guessing game. Any questions on this method? Great. We're asked to find the absolute maximum and minimum values of this function that they've given us, and we have the interval from -1/2 to 4. So, using the closed interval method, what's the first thing I need to do? I have to derive my function. Jessica, what's the derivative of this function?
3x minus, or to squared minus 6x.
Okay, so our derivative is 3x squared minus 6x. What are we doing with this derivative?
Setting it equals
We set it equal to 0. What does that do for us?
one of the critical numbers.
gonna help us find the critical numbers. So when I set this equal to 0, how do I solve? What do I need to do? I have to factor out. What can I take out of this?
X.
I can take out a 3x. When I take out a 3x, I'm left with x minus 2. What do I do here?
Set both equal to 0.
Set them both equal to 0. So where are my critical numbers?
X equals 0, X equals 2.
Okay, when else could I have a critical number? We found when the derivative equals
When it does not
Zero.
exist.
when it does not exist. Is there any value when a polynomial does not exist?
No. 'Cause
No.
It's continuous everywhere.
Good, because this goes back to what we talked about in chapter 2, where there are certain functions that are continuous everywhere. If a function is continuous everywhere, it's not going to have a point where it doesn't exist. So just keep in mind, like we talked about those at the beginning of the semester, those are things you need to carry throughout the class, is knowing that a polynomial is continuous everywhere, so I don't need to check for points where it doesn't exist. Rational functions, we know the denominator can equal 0, that kind of thing. But understand where that's coming from. Okay, so it doesn't exist because polynomials are continuous everywhere. So these are my critical numbers. What do I do now? I'm trying to find absolute maxes and mins. I have this function. They've given me an interval to look at. Okay, I'm plugging into the function. What values am I evaluating my function at?
0 and 2.
0. Is that it? If I'm trying to find absolute maximum and minimum values,
We also have to do the endpoints of the interval.
you have to also test the endpoints. So you're testing critical numbers and you're testing endpoints. What are we looking for when we test all of these points?
The highest and the lowest.
We're looking for the highest answer and we're looking for the lowest answer. So when I plug in 0 into this function, what do I get?
1.
I get 1. When I plug in 2 into this function,
-3.
negative 3. When I plug in, are we okay with this? You just plug it in here.
Yeah.
2 cubed is 8 minus 3 times 4 is 12 plus 1. How we get negative 3? F of negative 1/2 is going to give me a negative 1/8 minus 3/4, 3/4 plus 1. I need a common denominator of 8 throughout all of that. So 1 minus 6 plus 8 over 8.
5/8.
You guys like this?
Yeah, that's awesome.
Negative 5 plus 8 is 3 over 8. Tyler doesn't believe me, so he's checking. Yeah.
6.
It's all right, Tyler. I like my work to be checked. I make mistakes. And then f of 4, 64 minus 48 is 16 plus 1 is 17. So, absolute maximum value, what is it?
17.
F of 4 equals 17. The highest value that this is going to reach is 17. Absolute minimum.
F of 2 equals -3.
Negative
F of 2 equals negative 3. So this is my min. This is my max.
The other two be your local maximums or?
Well, as long as it's not an endpoint, it would be local.
Oh.
But we don't know.
We don't know that it changes direction, it might just slow down and keep going.
Yes. Yes. We'll get
So you
into
have
like
to test
more
that.
complex stuff. Yeah.
If we don't have endpoints, we only go use those The two critical
If you don't have endpoints, you can't prove. All you can do, the endpoints are necessary to use the extreme value theorem, and the extreme value theorem has to be let me look into that. Because I don't want to answer that incorrectly, like,
What if it's on the test?
it's not on the test, because the test is all about using closed intervals and like endpoints and all that. So, I'd have to look into that, I don't know. All right, any questions on this? Okay, steps to finding absolute maximum and minimum values. First thing we need to do.
Find
Okay, we have to derive, and what is deriving gonna help us get to?
critical numbers.
Critical numbers, where do we have critical numbers?
What
0
it does not exist.
or does not exist. Once we've identified these critical numbers, then what? Plug them into what? The original function, so make sure you're always going back to this function. You plug them into the original function, then what? Endpoints. And then once you have all of that information, what are you looking for? Highest and lowest. We got this?
Yeah.
Did we get this process? You guys ready for your assignment?
Yes.
You have a little bit of class time to get started on it. I recommend that you try some of it while you're in class. Make sure all of your questions are answered. And I'm gonna learn how to put this stuff up on my
Me to the YouTube, please.
Craft Academy.
I am technologically.
If you ever need help,
That would be- Okay, that would be awesome.